For decades, people measured robot progress by appearance. Bigger arms, smoother shells, more human faces. Yet the real question was never how a robot looked. It was whether it could perceive, adapt, balance, and act in the messy world beyond a lab bench. Then the hardware itself began to change. At Princeton, researchers built a robot without motors. No spinning joints. No hidden gears. Instead, the machine moved with heat. Its body was made from liquid crystal elastomer, a material that can be programmed at the molecular level. When warmed, it did not merely soften. It bent, contracted, unfolded in ways determined long before by the pattern of its printing. This changed the logic of design. Instead of building a rigid frame and attaching motors afterward, the movement was embedded directly into the material. A custom 3D printer laid down zones with different behaviors, like invisible hinges scattered through the body. When heat flowed through the structure, those zones responded predictably, and the robot could unfold, curl, or flap with a kind of mechanical memory. Even the electronics were not treated as separate parts. Circuit boards were integrated during printing, so the object emerged as one system rather than a pile of assembled pieces. Temperature sensors and closed-loop control gave it a way to monitor itself in real time, correcting its motion and repeating movements with surprising accuracy. One demonstration took the form of an origami-inspired structure that flapped like a crane. It was delicate in appearance. But the engineering behind it pointed to something larger, a future where robots are manufactured less like machines and more like living forms, with behavior shaped from the inside out. At the same time, another frontier was opening in a very different direction. Scientists created neuropods, living robots built from frog cells and integrated neurons. These were not metal machines pretending to be alive. They were biological constructs in which cells could develop into neural networks, linking with other cells that influence movement. As the neurons matured, the robot changed. It became more active. Its shape shifted. Its actions grew more complex. The result was unsettling and fascinating at once. In one case, motion came from heat embedded in printed matter. In the other, motion emerged from living tissue learning to coordinate itself. Both suggested the same conclusion: the future of robotics may not depend on making robots look more human, but on giving matter new ways to sense, respond, and evolve.